Okay, so let's first start off with the attendance. Okay. All right. So let me see. Let's see now. Okay, Muazzam Akhtar, you here?
Yes, Professor.
Yeah, thank you. Okay. Keidra, you're here. I saw you come in. Okay. Jabed Arafat, are you here? No. Okay. Akil. Okay, thanks.
Yes, I'm fine, I'm fine.
So you come in. Daniel, you came in. I saw you. Ahmed, you came in. I saw you.
I was also here last class, but I came late.
Okay.
Yeah, thank you.
Anthony, I saw you, right? Yes, I got you. Okay. Redwano, I saw you, correct? Yes, you're
Yeah,
here?
I'm here.
Great. Okay. Um, Mahima Hyatt, are you here? No. Okay. Okay. Aman Javid? Aman? Okay, great. Thank you. Fiola, you're here. I saw you. Okay. Just Rhythm Core, are you here?
Here.
You're here. Okay, thank you. Okay, Molly, you're here. Kuma, I saw you. Winston, you're here. I saw you.
Yep.
Okay, Mayan, you're here. Jason, you're here. Yvette Morales, you're here, right? I saw you. Leanna, I saw you come in. Rose, you're here. Okay. Israke, you're here now. Juan Osorio, are you here? Juan? Oh, okay, thank you. Okay, Rena Park,
Here.
you're here, thank you. Okay, okay. Adil Patel? Oh, great, okay, thank you. And Rishika, I know you're here, I saw you. Benedan, Anis, you're here, right? Yes, I saw you. Okay. Yeah, okay. Yasir, you're here? Yes, thank you. Richard Siegel, I saw you come in, yes. Sabrina Sultana, I saw you come in. Yeah, okay. Mohab Taha, you here? No. Ray Wang, are you here? Okay.
Yeah, I'm here.
Nicole Wang, I'm sorry. Got you. And page 2, Rebecca Wang. Thank you. And Douglas, you're here. I saw you come in. All right, great. Okay. All right, that takes care of that. Okay. We're required to take attendance for like 2-3 weeks, so.
Hello, Professor. I'm here. Ishak Nur.
I know, I got you. I saw you come in.
Oh, okay. Thank you.
Yeah, I clicked to admit you, so I know you're here. Okay. All righty. Okay, so let's first take a look at some of the homework. Let me get my sheet out here. Okay, so let me start bringing up that one. So Rena, you had the first problem, right? In 1.2, number 59A. So let me bring that. I'm gonna have to share. I gotta put, oh no. Okay. All right, and let me bring your homework up. Okay, 1.2, 59A and 61. Okay, Let me just get that out. All right. All right, so first, this problem 59A, they gave you this function. This is actually known as the Heaviside function. Heaviside was a very important guy, lived at the end of the 1800s. He was really an electrical engineer, but also a mathematician. He wasn't too worried about proofs, though. He was very practical. He's the guy who, because of his work in electrical engineering, they were able to lay the cable under the Atlantic to carry electronic messages in the 1890s or so. Namely, in those days, to carry telegrams, Morse code. He was the one who figured out and solved the problems with insulating the wires properly. So he turns out to be an important guy. He also had a lot to do with Maxwell's equations, which if you continue in physics or math, you'll hear about. But in any event, so they gave you this function defined in pieces. H of t is 0 if t less than 0, 1 if t greater than 1. All right, so what did you do for this? Rena?
Yes, Professor. So for that, I just drew a graph, and because t is going to be 0 if t is less than 0, so I just put a hole on 0, so it would indicate that it's going to be 0 for y, and it's going to be 1 if t is equal or greater than 0. So I just put a
solid circle or a dot.
Yes.
Yeah. Yeah, and this continues to the right infinitely out. The one thing, no, I don't want anyone misled by the picture here. This continues all the way along the negative axis here to minus infinity, okay? Because this function equals 0 if t is less than 0, always. If it's -1, -2, -3. I know it's hard to draw when it's overlapping the axis, but don't everyone be misled. This continues. This should be like a very thick line. It's part of the graph going out that way.
Professor.
Okay, so this is an example of a kind of function that we saw in the example I gave last time. And I also asked, have to make a comment here. Since this thing is a function of t, then the horizontal axis is now the t-axis, not the x-axis. Now, I know everyone's accustomed to using y as a function of x, and so they put x on the horizontal axis and y on the vertical axis. But there's nothing sacred about x and y. It's just that those are the most common ones we use and the ones you tend to learn first. But if you have a function, like say here, y is a function of t, that's what this is, then the horizontal axis is the t-axis. There's no x's in this problem. So you would label it as the t-axis. You wouldn't put an x here because there is no x in this problem. It's t, okay? There's nothing sacred about using x for the horizontal and y for the vertical. It's whatever the problem hands you, okay? In theory, you could have been given this as a problem. W is equal to h of t. In that case, you would label the vertical axis as w. That would be the vertical axis. It doesn't change anything else, doesn't change any theory or anything, okay? But as I said, you don't be rigid here. There's nothing sacred about using x and y. Very often we use other variables. In fact, in things dealing with time, we typically use t to represent time. So the label here shouldn't be x, it should just be a t, okay? All right, now I also asked you for practice to calculate the limits here. What's the limit as t goes to 0? So what's the story there?
So because t from the negative part is approaching to 0, I labeled it as 0.
Right, so the limit from below is 0, correct?
Right, and the t from the the limit from the positive side approaching to 0 is going to be 1.
Right, it's approaching 1. That's
Right.
correct.
Mhm.
And as we saw last class, what the function actually equals at t equals 0 is irrelevant in terms of these limits. So what's the final conclusion? The overall limit is, this again should be at t goes to 0, is,
It's not going to be defined.
right, it doesn't exist, because a limit only exists if it's going to be the same on both sides. Otherwise, we say there is no limit, it doesn't exist at all. Okay?
Right.
Okay, very nice. Sounds pretty straightforward. Okay. And by the way, this is a real function used in electrical engineering. In case you just thought the example I did last week with the holes in the graph and whatnot and the jumps, in case you think that that's just made up problems for practice, no, these things really come up in real life applications. Okay. All right. And then you also had this problem, 61. Okay, so 61 gives you two functions, a function f and a function g, and they want you to find the composition, f composed with g. All righty, so what's story here?
So because it was indicated that the both f and g functions were both linear, I just assumed that b1 and b2 are just going to be numbers.
Well,
And
yeah,
m1,
right.
yeah, m1 and m2 are going to be numbers as well. So for me, I remember to find the slope is for the composition first. I did that first, and then I put gx into the x of the f function, which
Right,
gave
right. That's how you calculate f composed with g. It's f of g of x. This means wherever you have an x in the f function, you replace it by whatever g is. G it's in its entirety. And this is very nicely written the way you did it here. From f, we have the m1. Then we have an x which has to be replaced by g, which would be m2x plus b2. That went in parentheses here. This is very nicely written out. And then you still have the plus b1 at the end. Okay. And then you end up with this, m1, m2 times x plus m1, b2 plus b1. And this is very nice what you did here. These are numbers, that's correct. m1, b2, b1, these are all numbers, okay? And this is a beautifully done, and you made the correct and important conclusion here. What happens here is that what this is telling us is that if we take the composition of two straight lines, because f and g are both straight lines, they're in the classical form of mx plus b. When you take the composition, you get a new straight line. Because if you look at this and don't get intimidated by all the symbols, this composition here is basically some number m times x plus some other number. In other words, all of this here, m1, b2 plus b1, this is all numbers. And when you add them all up, you're left with one number. That would represent b. So the composition function is a straight line. It's in the form of mx plus b, where m is m1 times m2, okay? And whatever this mess calculates out to be, that's b for the new line. Okay, don't get thrown off by the way sometimes these things look. You have to stand back. Don't lose the forest from the trees. What you're staring at on this line, on this line of paper here, is that this is the equation of a straight line. Okay, just because there are two symbols in front of the x and there are two sets of symbols afterward, that doesn't change anything. You have to look at the big picture. This whole thing multiplying the x is a number. This whole thing after the x, this whole expression with the plus in it, is some number. A number times x plus another number, that's the same as mx plus b. That's the equation of a brand new line. And you made a very interesting conclusion here that the slope of this new line, when you make this composition, is actually the product of the original two slopes, m1 and m2. And that's going to turn out to be very important in actually the next section that we do. A few sections down the line, you're going to see me come back to this exact thing here. That's going to turn out to be a very important observation. That's one of the reasons I like to assign this problem. Okay, but the other take-home message here is to recognize what you're looking at and don't get thrown off by a mass of symbols. When all is said and done, this entire thing here, my arrow is simply in the form mx plus b. It's a straight line. Okay, you got to get into that habit. Don't lose the forest from all these trees here. Okay, that's a very important point. Okay, all right. So thank you. That was very nice.
Thank you.
All righty. So now we move on. Nicole, you had 1.3 number 4. Okay. Let me pull that up. Oh, this was one of these graphs. Okay, so this was very similar to what I did in class. I guess I need to magnify this up so we can all see. Okay. All right, so they gave you this graph. Well, you know what? Let me enlarge this whole thing and see if I can make this bigger for everyone. Okay, so that's a little bit better. And then they wanted to calculate a whole bunch of things, just like I did in class. So the first thing was the limit of f as x goes to 2 from below. So what's the situation there, Nicole?
So the first one is the limit of 2 as it approaches from the left side. So on the graph, it would be approaching to 3. And then for the second one, it's approaching.
Well, let's solve a little bit. Yeah. So we're approaching x equal 2 from below. That's what this minus sign means there. Okay.
Yeah.
And if you're walking along the curve as you're approaching x equal 2 from below, and you ask, where is the y value headed? It's headed right here. Okay. And that corresponds to y equal 3. So this one-sided limit is 3. Okay. Now they're asking you, what about as x approaches 2 from above? What's the situation there?
So it would be the function as x approaches 2 from the right side. So
Correct.
it would be 1.
Right. Because as you come to 2 from the right, you're walking down the curve, you see you're approaching this point where y equal 1. So this one-sided limit should be 1. And now what's the overall limit as x goes to 2?
It wouldn't exist because the two limits from the right and the left are different.
Perfect. That's exactly correct. Okay. It's again, this is similar to what I went through with you the other day. All righty. Okay. These two limits are not, the two-sided limits are not equal, so the overall limit does not exist. And by the way, what is f of 2? What is the y value on x equal 2 for this function?
It would be 3 because,
Right, because
there's a point there.
right, this is a solid dot. It's a little hard to see here, but this is an open circle. That means the y value, that tells us the y value is meant to be this. Okay, so when x is 2, y in fact is 3. And once again, we see, as I stressed the other day, that the limit and what the function actually equals at a certain point have no relationship to each other necessarily, or they can be completely different. Okay, thanks, that was very good. And then they ask, what's the limit as x approaches 4? So what situation here?
So I looked at the limit from as x is approaching 4 from the left, and it would be 4. And then I looked at it
Right.
from the right and would also be 4 since both limits from the left and the right are the same and equal to 4. The overall limit would be 4.
Correct. But what is f of 4 actually?
It doesn't exist because there's an open circle there.
Right. So that's right. There is no y value. Yeah, usually this is correct. Usually the term we would use here is we'd say the function is undefined. It's a little funny to use this word, doesn't exist, but I mean, it's correct. But more commonly in the book, it'll say the function is not defined at x equal 4. That means for x equal 4, there's no y value. Okay, it's correct to say what you did. Okay, but once again, this is sort of similar to the kind of problem we did the other day in class. Very important concepts here. The fact that there is no y value for x equals 4 has nothing to do with the limit. That limit exists, and they're completely unrelated issues. Okay. All right, so that's very nice. Okay. All right, that was number 4. Guys, as I said, you should really look at all these similar kind of graph problems at the end of the section in the book, in this section, and really, really learn them well. Okay, that if you know them, you're in good shape. Okay, next, 1.4, we have number 12. Okay, let me bring that up. Okay, thank you. That was very nicely done. 1.412. All right. So this looks good. Okay. So Ishraka, what did you do with this one?
So yeah, the limit of the equation is 4. So I first inserted number 4, and
Right.
on the top and the bottom comes 0, which is undefined. So
0, right.
I have to do the equation. So I factored out the x's and on the top,
Right.
yeah, which leaves me with x and x minus 4.
Yeah.
And from on the bottom I did try to do the other factoring which gives me similar equation on the top and the bottom, like x minus 4.
Right. So
I
but
can,
before the crossing out, you have x times parentheses x minus 4 on top. The bottom
Yeah.
eventually factors to parentheses x plus 1 times parentheses x minus 4.
Yeah.
And these two terms will cancel.
Yeah.
Okay.
And that leaves us with x on the top and x plus 1 on the bottom. So now if I insert 4, it comes out as 4 by 5.
4/5, right. So this is correct. This is what the limit is going to equal. Again, I mentioned, it's not crucial if you remember it, but that the principle here is that this function x over x plus 1 is almost the exact same function as the original one, but there's one big difference. The original function doesn't exist at 4. This one does. So we use it to tell us what the limit is. It's the same thing as x squared over x versus x. Okay, the key thing you really have to know, the bottom line, is simply when you get 0 or 0, you got to do something because that's not an answer. And the usual first trick is to factor and simplify. The only other comment I have here is, and this is going to be very important, we have to be careful writing full equations because this is a sequence of equations here. So these should all be equal signs, and you need to include them so people can follow exactly what you're doing. All right. So these arrows mathematically mean imply, but what you really need here are just equal signs. There should be an equal sign here, here, here. Okay. You just can't have a list like I sometimes see of lines here with nothing from one line to the other. You want to indicate that these are all equal. And in fact, this limit is the same equals this, equals that. That's fine. Okay? That's the only comment I would make just about notationally. All right? Okay, so that was very nice. All right, then we can move on to Daniel. You have number 18, 1.4. All right. So can I move this up? Okay. All right. So this was problem number 18. Evaluate the limit as h goes to 0, 2 plus h cubed minus 8 over h. Okay. So what'd you do here, Daniel?
Do you hear me?
Yes. A little louder, though. Speak up a little louder.
You hear me now?
Okay. Yeah.
Okay. So first I tried to plug in 0, and that didn't work, obviously, because 0
Okay,
not.
Daniel.
Yeah.
Can you just speak a lot louder? It's not coming over so clear. Yell if
What
you
about
have
now?
to.
What about now? Is that better?
It's still very hard to hear. Just yell or
Okay.
something.
Okay, so basically,
Raise your voice.
I first plugged in 0, and
Okay.
0 obviously doesn't work in the denominator, so because it's undefined, so it cannot work.
Whoa, hold on. The fact that the bottom is 0, that fact alone doesn't mean it's necessarily undefined, and it doesn't necessarily mean you don't have a limit yet.
No, yeah, I'm
going
just
to
saying
see
that
that.
the fraction in that form is not defined. So what I did was
But just slow up. You understand it and know the answer, but we're going over it for everyone else.
okay,
The problem here is you're getting 0 over 0, because here you get 2 cubed is 8 minus 8 is 0. That's the problem. Simply getting a 0 on the top or simply getting a 0 on the bottom is not necessarily an issue with limits. What is a problem is 0 over 0. That means you're going to have to do something to evaluate it because it doesn't give you any answer. Okay? So there's a big
Okay.
distinction. Simply getting 0 on the bottom by itself doesn't necessarily mean you're going to have to do much more work to get an answer. We'll come to that soon. We haven't really done examples of that. The problem is with 0 over 0. That's why this is a problem. Okay?
Okay.
All right. So once you see you have 0 over 0, what did you go ahead and do?
So once I got 0 over 0, since that wasn't gonna show us what the actual limit is, I basically kind of did something similar to a conjugate, but Professor mentioned in the email that it's not exactly a conjugate. But basically, I just multiplied the top and bottom of the fraction by basically the reverse of the original.
No. Let me interrupt for a second. You have the correct work here, but what you're saying is not what you have here. You're jumping ahead. Let me slow you up for a
Okay.
second. This is not the
Mhm.
conjugate. That's number one. Remember, the
Mhm.
conjugate the example we show was when you have the square root of something plus a, and then you multiply top and bottom by the square root of the same thing minus a. That's what we mean by conjugate. Okay. What's happening here is far simpler. Okay. All you're doing is cubing out 2 plus h cubed. That's all you're doing here. And then simplifying the result. That's the only thing you're doing. You're not multiplying top and bottom by anything at all. All right? It's actually simpler than you're putting it in.
Oh,
Okay.
actually, I was looking at my work and I had a different version. Sorry, that was
Okay. What's up
crossed it
here
out.
is
Yeah, that was
correct right now. Okay.
yeah.
The
Okay.
first thing
No,
you got to do is just cube it out.
yeah,
And
basically, yeah.
then you simplify what you get. Okay. And it boils down to this. The work is basically correct. H cubed plus 6h squared plus 12h on top. Of course, you still have the h on the bottom. So this is perfect. All you're doing is algebraic work. You're cubing it out, which is a little messy, but you got the right answer. And you're combining the terms on top. And now you have this fraction. This fraction is identical to the original one because you simply cube that out. And then what you do, this is the key part.
I what's it called? After I cubed it out, I was able to distribute the h out, one h out of the entire thing.
We would say
And
you factored it out.
sorry, you factored it. Yeah,
Yeah.
factored it out.
The
And
opposite of distributed, right? Okay.
yeah,
You notice there's an h in each term. You factor it out. Great.
yeah, I factored it out, and I basically was able to cross out an h from the top and the bottom since they
Right.
divide out
That's
into
right
one.
here. And that just leaves you with this much simpler term to deal with: h squared plus 6h plus 12. Right?
Yeah. And
Exactly.
then I was able to plug in 0 and finally get a number that showed an actual limit.
Okay. Let me just slow up for a second. So yeah, this is correct. You're simplifying it down. So everything here is algebra. So the way this is written, though, I got a problem with, because this is not the way we write it. Everyone's got to look at those examples in the book. I think they're on page 39 or so. You generally got to look at the example in the book. All these things always have to be written out fully with equations, like the last problem was. So if you start with this thing, then what you need is a chain of equal signs. If you want to do the algebraic work on the side, that's fine. But the next thing here underneath this should be equals limit h goes to 0 of this, h squared plus 6h plus 12. Okay?
So I'm writing what I got in the end as the equation of the problem.
But no. You're leaving out all the steps. Okay? You don't just plug in 0. What you're doing here now is taking the limit of this expression. Now, this particular expression, to evaluate the limit, all you have to do is plug in 0. There's not too much to say about that. We're going to go over more of this today. But sometimes at this stage of the game, after you do algebraic simplification, you can't just plug in 0. You could still be left with 0 over 0, but it may be that you know some other way to do the limit, okay? So I'm just being picky here, but it has to be written carefully. You need a chain of equals terms, just like in the last problem. And we don't plug in so fast. What you need to write eventually from here, the next line should at least be equals limit h goes to 0 of parenthesis h squared plus 6h plus 12. The limit of that is simple because in that situation, it's a polynomial. All you have to remember, we said all you have to do is plug in the number. So that's true, okay? The work is correct and the answer is correct. It just needs to be written out a little more formally and carefully, okay?
I'm not sure what you mean by that. Like, I'm not
It
sure
has to
what
be-
exactly
Well,
I'm
did
writing
you look
out.
at the examples? Did you look at the examples in the book? You see the way they're written out? That's what your examples have to look like. They just can't be a mess of plug something in. You have to have a chain of equal signs, like the last problem we went over, from the beginning all the way to the end. And what you're taking at the end is the limit of this thing. Okay? We're going to do some more problems today. All right? It's okay to do the algebra on the side, but where's the work here? I mean, that's a problem. And it is technically incorrect to say just plug in 0 because not all functions, when you simplify, are going to let you just plug in 0 still. You may have to do more work. We're going to probably get today to doing a certain special limit, very special limit, where when you simplify and everything, you still get 0 over 0, but you don't plug in. There's something different you do, okay? So you got to be a little bit careful on how you're wording this, okay? But in this problem, you get a polynomial at the end. And I said the other day that when you get a polynomial, you plug in 0. Okay, look, everyone's got to look at the problems, the examples in the book, okay? And the way I write it out. That's what your work has to look like. I know there is an instructor, I won't say who teaches often 141 and 151, who takes off 8 out of 10 points if you don't have a chain of equations with equal signs with the word limit there. I'm not joking. I won't say who, but there is someone who would take off 8 out of 10 points, even though all the work is correct.
Oh, so you're saying that I just have to, each time I have like a new equal sign showing more work, I have to just add the limit sign and everything?
Yeah,
with that?
but when you, right, because, and then you see where my arrow is? You end up with the limit of this.
Mm-hmm.
And it just so happens that in this kind of limit, since this is a polynomial, that's when the next step is equals that, because it's true. All you have to do is plug in. I'm saying you're being a little too cavalier, because sometimes you don't have a nice polynomial where you can just plug it in. Sometimes you get a function down here, a new thing, which although it's simplified, still gives you 0 is 0, or you got to do something different and plug in. Okay, so that's what it bothers me. You got to be a little bit careful. Okay, all righty.
Okay.
It's correct. It has to be written out more neatly. Okay.
Yeah. Okay.
All right,
Yeah.
that's all I'm saying. All right.
Okay.
Very nice.
Thank you.
Okay.
Professor?
So, any questions on this?
Yeah, Professor.
What? Speak up. Yes.
For this one, for step 2.
Oh, okay. I cannot hear you at all. You got to speak way louder, please.
Can you hear me now?
Let me raise my microphone.
Hello? Can you hear me?
Okay. Yeah.
Okay, for what Daniel did for step 2, I just factored. Would that be, and I obviously got the same answer. Would that be an okay way of doing it?
What do you mean you factored?
So essentially what I did is I did 2 plus h times 2 plus h, and then I got an answer. And then I multiplied it by another 2 plus h minus 8.
Okay, well, first of all, whoever is crunching and has their mic on, you got to stop that. I can't hear. Okay, look, what you're describing already is not factoring. You're multiplying it out. Look,
Yeah.
someone has got to turn their microphone on. Whoever's eating potato chips, whoever you're eating, turn off your mic. Good God, come on. Okay, what you're describing is not factoring. What you're describing is multiplying it out. You first did 2 plus h times 2 plus h.
Yeah.
Then you took the result of that and multiplied it again by 2 plus h, correct?
Correct.
Okay, that's not what we refer to as factoring. Factoring is when is leaving it, and this would be a factored version of it. This is factored
Okay.
already.
Mm-hmm.
I'm picking on your terminology.
Yeah.
Okay, factoring would be if you started with the thing all multiplied out and then you brought it into a form like this. You multiplied it out, right?
Yeah, correct.
We'll make it even simpler. Don't worry about the word. You multiplied it out. That's what you did. That's technically not what we usually consider factoring. Okay.
Mm-hmm.
Okay, that's all I'm saying.
But
Okay.
is multiplying it out a correct form of doing it?
It's about the only way you can do this. I don't see how else you can do this problem. You have to cube it. The way you cube it is you first multiply 2 plus h times 2 plus h. That gives you the square, right? And then you got to multiply it by 2 plus h again to get the cube.
Yeah, but for whatever reason, mine seems like much more like longhand than this one.
I don't know, but basically that's this is what Daniel did here. He you see where my arrow is? He multiplied this 2 plus h times this 2 plus h, which gives him this term here.
Yeah, I skipped steps, so I did it in my mind. So
Daniel, let me finish here.
Okay.
This is fine. Let me clear up this confusion here. Daniel wrote this out. Cubing it means multiplying by 3 times. So what he did was he took the first and the second 2 plus h's, foiled them out, and he gets this term. Now he multiplies it by the third 2 plus h, and he didn't write in all the little steps in here. He simplified it. But this is what he did. He just multiplied it by itself 3 times.
Got it. Yeah. Okay, I got it. Yeah. It's the same thing. I just wrote out all the steps. Got it.
Right. Okay. All right. Everyone happy with that now?
Thank
Professor?
Yes.
I think I actually factored it and it worked.
But how? I don't understand. How could you factor this? 2
So
plus h is already factored.
I know. I consider 2 plus h as I replaced it by an a, and the 8 I wrote it as 2 to the third, right? And then there's a remarkable identity which says a to the third minus b to the third equals.
Okay, so you're talking about, okay, so you're talking about how you factor a cubic.
Yeah.
Okay, so you're using that formula. Okay, you can
Yeah.
do that. That's fine. I don't want to go there. That's most of us don't. Most people don't have that formula on their fingertips. Okay. Okay. All right. Okay. The simplest thing is just multiply it out. Okay, that's how anyone would do this problem normally. Okay. All right. Now, Yvette, you had number 44, right?
Yes.
Let me pull this one up. Okay, so this was another one of these pictures. Let me just see. Okay, doke. So they give you this function defined in pieces. G of x is x for if x is less than 1. You really should need to put the x in here. Okay.
Okay.
That's just a typo. G of x equals 3. If x equal 1, that's perfect. It's this. Okay, so this is defined piecewise. And now they want you to calculate a bunch of stuff and graph it. Okay, so first thing they want is the limit as x goes to 1 from below. All right, so this actually introduces a slightly new aspect. Up till now, the examples we looked at was to first graph out the thing. But normally you don't have to, and you don't normally take the time to graph it out. What you usually would do is just use the equations to answer the question. Okay, which it looks like that's what you did. Is that right?
Yes.
Which is good. That's even better. Okay, so we didn't do an example we want very little like this yet. We will. So the first question is x approaches 1 from below. So how'd you come up with that this one-sided limit is going to be 1? That's correct, but how'd you do it?
Okay, so I took the first and the third equation. So because as x, the first one says x less than 1, so we know that it's going it's approaching 1, and then from 2 minus x squared, there's the 1 as well. So that's between that. That's
Well,
how
that's going to give you that's going to give you the other sided limit.
No, yes,
gonna,
I know. But
yeah.
I meant like as that.
Okay, hold on. You're going a little too fast for everyone else. Okay, this is new, and this is you got it. That's fine. Okay, all right. In order to figure out what is the limit as you approach 1 from below, you look up here and you realize that anytime x is below 1, the equation is x equals x. Y equal x, I should say, right? Okay. So what you're really dealing with is the function y equal x as x approaches 1. Because you remember you're approaching 1 from below. Well, that means this encompasses everything whenever x is below 1. So this is the equation you need to say what is the limit as x goes to 1 from below. Because that's what this always is if you're below 1. And this tells you whenever you're below 1, y is equal to x. Okay? So that means since this thing is headed towards 1, this is going to be just 1. Okay? That's very nicely done. All right. And over here, didn't they ask you to do, oh, they didn't ask you to evaluate x approaching 1 from above.
No, they didn't ask that.
Okay, so, but that's something that technically you really sort of need to do, because when the function is defined in pieces, you got to be careful that you get the same limit on both sides. Your work is correct here. So let's just say a word about that. You're telling me the correct answer, by the way. I'm just pointing it out in more detail for everyone else.
Okay.
As x is approaching 1 from above, well, where do we have the situation where x is above 1? That's this term here. And this tells us that in that case, where x is approaching 1 from above, y is 2 minus x squared. Okay? And whenever x is greater than 1, that's what y is. So we use this to say, okay, so as x is coming closer to 1 along this equation, whatever the graph of this is approaching 2 minus 1, which is 1. So the limit on the right is also going to be 1. The limit as x goes to 1 plus is also 1. Okay? And that lets us conclude that the limit as x goes to 1 equal 1 is indeed correct. All right, let's take a second to look at this on the graph, since I know it's a little difficult. So when x is less than 1, y is equal to x. The graph of that is this straight line. Okay? When x is above 1, y is equal to 2 minus x squared. Now, 2 minus x squared is an upside down parabola. Okay, we'll accept this as a graph of that. It's a little more curvy, but okay. So when you look at it graphically, you see that as you're approaching 1 from below, you're approaching y equal 1. But when you're approaching 1 from above, you're also approaching y equal 1. So if you have the graph, it's a little easier. But generally speaking, you don't have the graph. What you got to do is work with the equations, which is equivalent. That's what you're going to have to get used to. So if you're below 1, y is always equal to x. As x goes to 1, what does x do? Well, x goes to x. X goes to 1. That's simple. As x is above 1 and approaching 1, this is the equation that governs what y is. And as this x gets closer to 1, this thing approaches 2 minus 1, which would be 1. Okay, and you're seeing the correlate here in pictorially. But you also have to get used to doing it by the equations alone. Okay? The work is excellent here. I'm just going into a lot more detail for the class, okay?
Okay.
All righty. Now, what about g of 1? Now they're asking you, well, what is y when x equal 1? And the answer to that is
3.
3. Because this is where you look. If x equal 1, y equal 3. So that's g of 1. And on the picture,
sorry.
Yeah, on the picture, it's missing. It should be right over here. For x equal 1, there should be a dot, a solid dot over here. So again, this is similar to what we looked at the other day. The curve comes up. The curve comes up here. This is an open circle because the actual y value is sitting all the way up here. Okay? That's perfect. That's nice. Okay, so there should be a solid dot there. All righty. Now we start dealing with 2. So now they want to know what happens as x approaches 2 from below. So what'd you do for that?
From x to below, I use the second equation as well, since it's a less than or equal to sign. And in the graph, I put a solid dot. So as it was approaching it from below, it was -2 when
Okay.
I grabbed it.
Right, because
Yeah.
okay, right, because when you're below 2, this is the thing that gives you the y values, 2 minus x squared. As this x gets closer and closer to 2, okay, you're going to get 2 minus 4 essentially, which should be -2. And that's what you get. All right, we'll look at the graph in a second. And if you approach 2 from above, well, this is now the equation that gives you y whenever x is greater than 2, okay? And as you approach from above, this is going to become 2 minus 3, which would be -1. So graphically, we see as x is approaching 2, from below, you're headed to -2, but from above, you're headed to -1. So the overall limit
It does not exist.
Does not exist, exactly, because it's different on two sides. And if we said, what is f of 2 actually? Well, to get f of 2, you look here and you see that for x equal 2, this is going to be the y value. So for x equal 2, you plug this in, you get 2 minus 4 is minus 2. So that's the y value. That's correct. That's graphed perfectly. Okay? All right, we're going to do a lot more of these because 98% of the time, you're going to have to get the limits only from the equations, really. So we'll look at more of these. This is a little more difficult to get used to. It's much easier to see it first as a picture. That's why the example I did the other day was in pictures. Okay? But that's very
Is
nice.
it okay if we get used to making the graph first, or should we know how to tell from the actual equation?
You absolutely have to know how to tell from equations, because many of the equations you're going to get here are just going to waste an extra hour on an exam trying to graph them all. You have to know how to do it from these. Okay? You have to. And you also need it for the next topic coming up after limits, which is something called continuity. You need to be able to do it from the equations. Okay? I mean, we can graph it on the calculator. We'll be using the calculator. I'll be showing you how to graph it to help you, guide you. But you absolutely have to understand how to do it from these equations. That's crucial. And we need some more facts and preparation to do that well. Okay, this problem was a little bit premature in that sense for you at this point. All righty. Okay. 1 second. There's one other problem which I'll come back to. 48. I'm going to come back to that. I don't want to spend time now. That's more of an interest problem. Okay. All right. Very good. So, any questions right now? All right. So, let me stop presenting. Okay. And let me get my notes out and we'll get going. This a little bit here. Okay. So we're going to get a little more formal now in some of the limit work we're doing. And let me go to the video. Okay, that's that. And all right. Okay, now. So everyone can see the this psychedelic wheel thing here. We're using to. Yes, everyone see this? I don't see how it's going to get much clearer. Anyone else think it's not clear? All right, let's see what it looks like when I start writing. This thing is getting me sick already, this stupid writing. Okay. All righty. So what we want to do now is we're going to look at some rules that are helpful for evaluating limits when you have the thing in an equation form. Okay. And most of these rules are very straightforward. So suppose you have two functions, f of x and g of x, and you add them up. Okay. And we need the limit of the sum. We want to know what's the limit as, say, x approaches some point A of this brand new function I get when I add them all up. Like, for example, f might be the function x squared, g might be the function sine x. So the function f plus g is simply x squared plus sine x. And so I want to evaluate what is the limit as x goes to some point A. So the answer here is very simple. you take the limit of the first as x goes to a, and the limit of the second one as x goes to a, and you add them up separately and you add them together. We've actually sort of been doing this without even thinking about it. We've been doing it automatically, okay? I mean, so for example, in this example, x squared plus sine x, say x is going to 0, you just do each one and add them together. We're making this fancier than it has to be. The book makes it very fancy. As x goes to 0, x squared goes to 0. As x goes to 0, sine x is also going to 0 because the sine of 0 is 0. So that's it. The book is kind of making a very big deal about these rules. And obviously the same is true if you do a subtraction here, okay? Another rule is, suppose I take something like x squared and I multiply it by a number and I get a new function, say 5x squared, and I want to evaluate the limit as x goes to 0. So the rule is you can bring the constant outside in front. That's 5 times the limit of x squared as x goes to 0. You just pull the constant outside. Again, we've implicitly been doing that up until now, which in this case is going to give you 5 times 0, which is 0. So you can just pull the constant outside. That's all that one's saying. And what about a multiplication? Same thing. If I have the limit of a product, I don't want to. Okay, I'm just gonna write it this way. A product of a function f times a function g. To take the limit, I take the limit of f and the limit of g separately, and I multiply them together. This is all straightforward stuff. I deliberately am not going to give you an example of that right now for a special reason. Okay, same thing if I have a quotient, and we've already kind of tried to do that already. If I have a limit of a quotient, normally you take the limit of the top and the limit of the bottom separate and just divide them, provided you don't get 0 over 0 or something like that. Okay, the book is just doing this very technically. It's getting very fancy. And what about the limit of x to some power n? Okay, that's, you just take the limit of x and afterwards raise it to the power of n. Let me give you an example of that, since I may be losing people here. If I want the limit as x approaches 3 of x squared, this says that basically I take the limit of x itself, which would be 3. As x goes to 3, x goes to 3, and then I square that. Okay, 9. This is very simple. It's straightforward. We're making a big deal about very, very little here. Okay, the book is just saying all of these things are justified. Okay. One other thing to point out, what about the limit of a constant number like 5 as x goes to 10? Well, the limit of a constant number is always going to be the same number, okay? If you think about this, this is saying the function is y equal 5. The graph of that is a horizontal straight line. So no matter what x you head to, like x equal 10, y is always going to be heading to 5 because it always equals 5. So this is straightforward. The limit of a constant number is just a constant number. As I said, the book is just making a big deal about this. All right, there's more than you need to. So, but let me just give you the example it gives. So suppose we need the limit as x approaches 2 of x squared plus 3x to the 4th plus 5. Okay. All those rules I just did simply say, well, I'll write out the detail, but we never bother, but I'll write it out. It says this is the same as taking the limit as x goes to 2 of x and then squaring it, plus taking 3 times the limit of x and then taking it to the 4th power as x goes to 2. I'm sorry, I ran out of space here. Plus the limit as x goes to 2 of 5. I'm sorry, I ran out of space. This should be on one line.
What was x going towards for the 3
Two.
times lim x to the 4th?
X is going to 2.
No, for the one all the way in the
Two.
end.
It's always
Yeah,
going
that one,
to 2. That doesn't change.
Okay.
I'm just showing
Oh,
you how
okay.
you evaluate it. You just split it up into pieces. You're never going to write this out. Okay, I'm just showing what the book's the point the book's trying to bring across, but no one ever writes any of this junk out. It's just saying it's okay to just plug in, basically. That's what it's saying. So the limit is x goes to 2 of 2 is simply 2. So he's saying, so that's 2 squared plus 3 times. The limit as x goes to 2 here is 2. The limit as x goes to a 5 is always 5. That never changes. That's a constant number. So this is 4 plus 3 times 16 plus 5. 2 to the 4th is 16. 2 times 2 is 4. So 8, yeah, 16. Okay. That's it. He's just saying you just plug it in. No one writes all this junk out. You just plug it in. That's 2 squared plus 3 times 2 to the 4th plus 5, and you're done. I'm just being very, very technical here. Okay. All right. Now, okay. All right. Now we're going to do something which is an important new idea here, and this thing is. Okay. Suppose we have 2 functions, f of x and g of x, and suppose it's always true that f of x is less than g. In other words, I have a function f, and here's another function g, and suppose it's true that g is always greater than f. Remember, when we say g is greater than f, we mean the y value is 0. For each x, the y value for g is bigger than the y value for f. Okay, suppose I take the limits here. What does this tell me about the limit of f of x as x goes to a compared to the limit of g of x as x goes to a? In other words, if f is less than g or g is always bigger than f, and I take the limit of both of them to the same point, what's going to happen here? What do you think is going to happen to the limits? Take a wild guess. G is always bigger than f. So what do you think the limit at the same point is going to be for g versus f? Yeah, you would assume that g should be greater, right? So it should follow immediately that that's true. And that's almost correct. There's one little problem. It may work out that the limits are actually equal. And I can't yet show you an example of this. I have examples, but you don't know enough to really see the example yet. Okay? So this is something you just have to kind of keep in mind for a moment. Okay? It can work out that the limits end up being equal. But in general, if f is less than g, the limit of f is going to be less than limit of g, but they can occasionally end up being equal. As I said, I can show you simple examples, but you haven't learned enough yet to understand the example. Okay, so you just have to keep this in mind for a moment. All right, but now we come to something that is a little more important, and here it goes. Suppose now I have three functions. I have a function f, and that's less than a function g, and that's less than a function h. Or they could even be less than, greater than or equal to, it doesn't matter. Whether it's exactly greater than or greater than or equal to is irrelevant. Here's an interesting point. Suppose I tell you that the limit of f as x approaches a certain point A is some number we'll call L. And suppose I tell you that the limit of x of h as x approaches that point is also L. So we consider some point, we say, what's the limit as x goes to A of these three functions? And suppose the limit for f is L, and the limit for h is also L. In other words, this f is going to L, this h, the y value, is going to L. So there's a major conclusion to be drawn here. If f and h are both approaching L, and the function g is stuck between them, there's a very obvious conclusion here. Anyone want to hazard a guess what the limit of g would have to be?
L.
L, yeah, it also has to go L because it's stuck between the other two. If f is always less than equal to g is less than equal to h, if f is going to L and h is going to L and g is stuck between them, it also has got to be going to L. And the book calls this the squeeze theorem. Okay. All right, and that's an important theorem which we're going to be learning, which we're going to be using in a minute. Okay, that's about the only new things here that surprise you or whatever are this inequality theorem. Remember, it could end up being equal to also, and this squeeze theorem, that's new. Okay. All right, so we're going to actually use this, and let's do an example of the squeeze theorem. And the squeeze theorem comes up very commonly with a trig function, with trig functions, and you'll see why in a sec. Let me just put this piece of paper down, and let me get a fresh piece of blank paper. Okay, so here's a classic example. Evaluate this limit. Limit as x goes to 0 for the function x squared times sine of 1 over x. Okay. All right. Now, if you try to plug in here and say, okay, if x is going to 0, x squared is also going to 0. That seems like okay. And then you figure you just multiply it by the limit of sine of 1 over x. But there's a big problem here. We looked at this the other day. As x goes to 0, 1 over x is becoming infinite. Remember we said the other day, if you have a fraction and you keep the top fixed, but you keep making the bottom smaller and smaller and smaller, the whole fraction is going to go to infinity. And then there's another issue here too, which I'll skip for a moment. And the sign of something going to infinity, that limit doesn't exist because sine just keeps oscillating. It's not going to any one place. So if we try to work this limit out just by plugging in, we don't seem to get a definite answer here. We don't know what's happening. This is why I said you have to be a little careful about saying just plug it in. Okay? So this kind of problem, though, is perfectly set up for the squeeze theorem. Anything with a sine or a cosine often comes down to squeeze theorem. And the reason that is true is because there's something you always know about sine or cosine, always. Namely, that they're always stuck between -1 and +1. -1 is always less than or equal to the sine of anything, and that's always less than or equal to +1. Sine and cosine, no matter what you plug in, are always greater than or equal to -1 and less than or equal to 1. Sine is always stuck between -1 and +1. If you look at the graph, that's exactly what's happening, right? It's always stuck between -1 and +1. And my drawing's awful, but so this is true for sine and this is true for cosine. And this makes it a very good starting point for squeeze theorem problems. So let's see how we can use this and squeeze theorem to answer this limit. So we know -1 is less than or equal to sine of 1 over x, less than or equal to 1. You don't have to think about what's going on in there. We know this is always true. Okay? All right. Now, we're not interested in sine 1 over x. We're interested in this whole function, x squared times sine 1 over x. So how am I going to convert this into an x squared times sine 1 over x? Well, I just have to multiply through this inequality by x squared. So I'm going to get minus x squared is less than or equal to x squared times sine of 1 over x is less than or equal to x squared. I'm sorry. Okay. All right. By the way, what do I have to be careful about when I multiply across an inequality? Someone tell me, what do I have to worry about when I multiply across an inequality? Sign, yeah. So let me explain this out. Thank you. That's correct. If A is less than B, and I multiply both sides by some number K, is KA always less than KB? The answer to that is only if K is positive. If you multiply an inequality by a negative number, it reverses the inequality. 2 is less than 3. If I multiply both sides by a positive number, say 2, we'll get 4 is less than 6. But if I multiply by a negative number, like -2, I'm going to get -4 here and -6 here. But -4 is greater than -6. So when you multiply across an inequality by a negative number, it reverses the inequality sign. You always have to be on the lookout for that problem. So over here, in this example we're doing with limits, you can't just say I'm multiplying across by something and the inequality is staying the same. You got to be able to say I'm multiplying through by a positive number, because if I'm not, I'm going to have to reverse the inequalities. Well, I multiplied through by x squared. What do you know about x squared? What happens when you square any number, real number? Can it be negative? No.
They are always possible.
Yeah, it had anything squared. Anything squared is always greater than or equal to 0. When you square a number, you're never going to get 0. It's positive and error. So this is fine. Multiplying across here didn't change inequalities. Now let's take the limit as x goes to 0. We're going to take the limit straight across, minus the limit of minus x squared as x goes to 0. Limit of this whole thing, x squared sine 1 over x, less than or equal to limit of x squared as x goes to 0. We're using this technical rule I mentioned a couple of minutes ago, that you take a limit, it doesn't change the inequality. Now, what is the limit here as x goes to 0 of x squared? Well, as x goes to 0, x squared is also going to 0. So the limit here is 0. What about over here? Well, as x goes to 0, x squared goes to 0, minus 0 is still 0. So this is also going to 0. So the squeeze theorem now tells us if this is going to 0 and this is going to 0, the thing that's stuck between them must also be going to 0. Okay? All right. So this is a classic example of the squeeze theorem. It's not obvious what the original limit is until you work it out. I can give you a very fancy, advanced reason why I know without doing any work this one's going to be 0, but you wouldn't know it. So you're stuck with the squeeze theorem at this point. Okay? All right, so this is a classic example of the squeeze theorem, use of the squeeze theorem. Okay? All right, so as soon as you see a peculiar theorem in a homework problem that involves a sine or a cosine, you know you can always resort to this, and this is always the starting point. Sine or cosine are always stuck between 0, -1, and +1. So the squeeze there. Okay, so Yassi is asking about, does this work if there's no overall limit? The function here does have a limit, an overall limit. And the answer to that is 0. It's one piece of the product that's a problem. But you can't conclude from one piece of the product what the whole thing is when you multiply it together. Okay? That's what I'm saying. This one really, this piece only by itself doesn't exist, but when you multiply it x squared, something else is going to happen. What's really happening here is that the x squared term is going to 0. It's dragging the whole product all the way down to 0. If you want a more detailed explanation, okay, don't worry about it. Okay, this is bounded for people who know what that means. Okay, this is always between -1 and +1. As that goes to 0, it's going to get smaller and smaller and smaller and smaller and smaller. All right, don't worry about that. Just know the squeeze theorem. All right, now we're coming now to a very important limit, which we always prove. The book proves it. I'll prove it also. And this is a very famous limit. Limit as x goes to 0, sine x over x. Okay? Now, if you just try to plug in here, you're going to get 0 over 0. So that means we don't know what's going to happen. Okay? You got to do some work to figure this out. All right? So this requires actually a geometric proof. And let's set up the geometric proof. Let me see if I have enough time. Let me see if I can do it. All right, so this proof is in the book. Let's try to run through it. The book likes to use the letter H instead of X for this proof. I know why, but we'll follow what the book does. Doesn't matter what letter you use, there's nothing sacred about X. All right, so we're going to draw a picture here. And what we're going to do is we're going to take a little piece of a circle of radius 1. Okay. And we'll raise, the origin is here. We'll call this point B. We'll call, what does it call this point? Q. And this point is P. Okay, so here's what we're interested in. This is a section from a circular radius 1. That means this length is 1 and this length. In other words, OB and OP are radii of the circle. I'm not drawing in the entire circle. I'm just taking out a little slice of the circle. That's what I'm trying to draw over here. And the circle has radius 1. Okay? And we're going to call this angle H. Remember, angles are always measured in radians. So we'll call it H. Okay? And we're also going to drop a perpendicular from P down here to the x-axis. And we're going to call this point over here A. Now, looking at the picture, I think everyone will agree on the following. The area of this triangle OAP, this right triangle here, is less than the area of the entire circular sector, the slice of the circle. There's certainly less area in the triangle than in the sector. And that area is less than the bigger triangle, which goes outside the circle. I think we can all agree those three areas are in that order. This area is smaller than the whole sector, which is smaller than the whole triangle. So let's write out what those areas are. So first of all, the area of triangle OAP, so that area of a triangle, remember, is 1/2 base times height. Okay. So 1/2 what did I write down here? I wrote this down in the. I have a mistake in my notes. I'm sorry about that. Okay. Okay. And I'm making it harder than it is. I have a mistake. I wrote it wrong in my notes. I wrote it backwards in my note, which is going to be confusing to everyone. Base times height. I'm sorry, I have to. This is reversing it. Oh. Yeah, okay. I see what I did wrong. Okay. All right, I made a mistake here. I drew this incorrectly. And I just wasted some time, not too much time. All right, I'm sorry, I drew the picture wrong. I'm sorry, I left out the chord here. We need this chord. That's what I did wrong. Okay, I'll tell you what. We're running out of time, right? No, what do we have until? One second. I don't want to start something that I'm not going to be able to finish here. I drew that wrong initially. That was my fault. Oh, wait a minute. We have until 4 or 5. I got time. Okay. I'm sorry. I left something out here. I drew this thing incorrectly. That's what's causing the problem. Yeah. Okay. All right. Let me redraw this a little better. Okay. So we're going to have this thing here. This is a radius of the circle out to B. Okay. I'm sorry. I drew the wrong picture. All right. And this is the circle coming upward. All right. And this is going to be the point P. That's still the origin. And what I want to draw in is the chord connecting P and B. I left that out before. That's a chord. We call that a chord in a circle if you remember the geometry. Okay. The rest of the picture is okay. I'm going to extend this up perpendicularly to point Q. All right. And these are the 3 triangles I want. I want OBP, this triangle in here. And we all agree that the area in this triangle in here is less than the area of this entire circular section, because you have this additional area if you want to look at the whole section. And that area is less than the area of this big triangle, OBQ. So we all can agree that the area of OBP is less than the area of the sector, and that's less than triangle OBQ in terms of area. I'm sorry, but I blew the drawing the first time around. Okay? All right, now let's start saying, what are these areas? Okay, so area of triangle OBP is indeed 1/2 base times height. One half base times height. Now, the base here is a radius of the circle, O to B. That's a radius. And we said this is going to have, the radius here is length 1. So this is going to be 1/2 times 1 times the height. But the height of this triangle is BP. Right? P. No, the height is along the perpendicular. I'm sorry. This is not necessarily a right triangle there. The triangle OBP, the base is OB, the height is A to P. You have to drop a perpendicular from P to get that height. And if we look carefully here, how do we get this length PA? Well, the length PA, if we look inside, this is now a right triangle. That's not the triangle we're originally dealing with. But using that fact, we can say that in this little right triangle here, the sine of h is equal to the length PA over 1, opposite over hypotenuse, right? So the length PA is sine of h. And that's the height. The height has to be measured, obviously, along a perpendicular. All right, so we find that the area of OBP, this triangle, OB to P, is 1/2 sine of h. Okay, so that's the first thing. All right. Now we're going to need the area. I'm going to skip to the easier one. The area of this big triangle, OBQ. That is a right triangle. I drew it as a right triangle. So the area, I'll come up to a new piece of paper for a moment. It's also going to be 1/2 base times height. And looking at the picture for OBQ, the base is OB, but that length is 1 because it's a radius of the circle. And the height is going to be the length of BQ, right? It's 1/2 times 1 times the length of BQ. Okay, and what is the length of BQ? If you look at the picture here, well, using some trig, the tangent of H is going to be QB over OB, right? Opposite over adjacent. So tangent of H is going to be QB over 1 because OB is a radius 1. QB, BQ. So we end up with the area of OBQ is equal to 1/2 tan H. All right, now, so we now have the area of this triangle formed by the chord. That's not necessarily a right triangle. That's why I had to drop the perpendicular. And we have the area of the bigger triangle. Now we need the area of the sector, the circular sector. Okay, so how do we get the area of a circular sector? So let me just take this to the side and review something for a second, in case you don't have that formula on your fingertips. Suppose I have, better yet, let me draw the circle. Suppose I take a circle and I just take a sector where the angle of the sector is theta. And I want to know what is the area of this sector. So you learned in geometry, we'll do this real quick. This becomes a problem of proportion. Okay, suppose the radius of the circle is r. Now, we know that if I take the entire circle, which will be 360 degrees or 2 pi radians, we get that for 2 pi radians, the area of the entire circle is pi r squared. Okay. If I'm only taking a slice of the circle, then it's going to be a proportion. Instead of taking 360 degrees, I'm taking theta degrees. It's going to be theta over the area of the sector. In other words, 360 degrees is to the entire area as theta is to the area of the sector. That's straightforward proportion, right? Solving for the area of the sector, the pi's cancel out, okay? And I've got the area of the sector is going to be theta times r squared over 2. What I just did was rederive the formula for the area of a sector. You don't have to know that, but I'm just filling in the details that are not in the book. Okay, so in our problem here, we have a sector where the angle is h and the radius is 1. So the area of our sector is going to be h times 1 squared over 2, which is h over 2. So those are the 3 areas. That's how you come up with the 3 areas of the 3 regions. All right, so let's see what we got. The area of this triangle OBP that's formed by the chord is 1/2 sine h. So we have 1/2 sine h. That area is less than the area of the sector. We just calculated the sector to be h divided by 2. And that area is less than the big triangle OBQ. The area of OBQ is 1/2 tan h. Okay? So this is what you end up with as an inequality. So if we multiply through by 2, we just get sine h is less than h is less than tan h. Okay? And tan, remember, is sine over cosine. So we get sine h is less than h is less than sine h over cosine h. Okay? And I now want to divide through by sine. So if I divide through by sine, sine over sine is going to give me 1. This will be h over sine. And this will be 1 over cosine h if I divide through by sine. Now I'm going to take reciprocals. This is a messy proof. If I take reciprocals, remember what happens when you take reciprocals to an inequality? If A is bigger than B, then 1 over A is less than 1 over B. That's what happens when you take reciprocals. So this is a review of a lot of algebra, geometry, and junk like that. So I take reciprocals. Reciprocal 1 is 1 is greater than sine h over h, which is greater than cosine h over 1. Okay? All right. So let me rewrite this up here now. we have 1 is greater than sine h over h, which is greater than cosine h over 1. It's a lot of work to get that little inequality. Okay. Now we're going to use the squeeze theorem. Okay. I now want to take the limit as h goes to 0, because that's what we're interested in. Remember, the original problem is sine h over h as x goes to 0, or sine x over x as x goes to 0. It doesn't matter what letter you're using. Well, the limit as h goes to 0 of a constant number 1 we saw before is just the number. The middle is sine h over h, which we don't know, because that would be 0 over 0, so we don't know what that is yet. And as h goes to 0, cosine h goes to 1, because the cosine of 0 is 1. So that's 1. So when we take the limit as h goes to 0, lo and behold, we see sine h over h is stuck between 1 and 1. So the only possible conclusion here is the limit as h goes to 0 of sine h over h has to be 1. Or we could say the limit as theta goes to 0 of sine theta over theta also is 1. Or you could say the limit as x goes to 0 of sine x over x is 1. It doesn't matter what letter you're using, it's always the same thing. How did the reciprocal for h is not 1. Reciprocal for 1 is 1. I don't see what you're asking. Where was the last sheet? Got it? Okay. Is that right? Okay, great. Okay. Now, okay. This is not an expected result, although this was a numerical example I did the other day. Because as I said, if you just try to plug in here sine x over x, you would get 0 over 0. But that's not what the limit is. The limit is 1. Okay, this was the numerical example I showed you the other day. No, I'm just showing you the proof. You don't have to learn the proof. I wouldn't ask you to do the proof. I'm just filling in the details in the book that are left out. Okay. All righty. You certainly must know the final answer, because this is one of the most important limits there are. It will be used all semester. It will be used, in fact, endlessly. It's one of the most important limits there are in calculus. Okay? All right, but sometimes it's given to you in a peculiar way. So let's look at a problem here, an example. Limit as x goes to 0 of sine 4x over x. Okay. When you look at this problem, at first you might think to yourself, well, this would be sine 0 over 0. Aha, that's 1. You may think that. But you can never make a conclusion like that, because the sine of 4x and the sine of x are different functions. You don't know that, okay? When you see a problem like this, though, you always have to say, well, how can I get this limit? And the answer is, listen to me, this is a practical tool for students. There is only one limit you know that looks anything like this, and that's the one we just learned, sine x over x. So the idea is to try to convert this into sine x over x, meaning that whatever inside the sine, I have to have the same thing on the bottom. That's what makes this work. So what I need to do here is multiply top and bottom by 4. 4 times sine 4x on top over 4x on bottom. Multiplying top and bottom by 4 obviously does not change anything. Now, I'm going to show you a detail which I'm not going to require to put in on an exam, but really should be. But here's the thing. We now have a new limit. Sine of 4x over 4x as x goes to 0. Since we have the same thing inside the sine as down here, you might guess that that limit is 1. That this thing should be the same as the original, because I have the same thing inside the sine as on the bottom. You can't jump to that conclusion without making a good argument. That conclusion is correct. I'm going to show it to you once. I won't make you do this on exam. Some instructors do. And the idea is to say, let theta equal 4x. I'm just going to show you these details, which the book doesn't show, but some people will require it. I'm not going to ask you to do it. So if that's the case, then the limit of sine 4x over 4x as x goes to 0 is the limit of sine theta over theta as theta goes to something. Now you got to be careful. When you make a substitution, the variable is going to a different number, maybe. Well, if you look at this equation, theta equal 4x, as x goes to 0, this equation tells us theta also goes to 0 from this equation. Because 4 times 0 is 0. So in fact, if x goes to 0, theta goes to 0. Now, if you look at this limit here, that is the identical limit we just learned. That is 1. This is the proof behind that. So this is 1. I won't ask you to keep reproducing this on the exam, okay? It's good enough to get it into a point where the sine of something, you get the same thing on the bottom, it's going to be 1. So now I have this, I have limit x goes to 0 of 4 times, I'm going to rewrite it this way. And we just showed that this piece is going to be going to 1. So the answer will be 4 times 1, 4. That's the final answer. So let me just recap the bottom line here. Whenever you see a limit that looks anything like this with a trig or something, there's only one limit you know that you can use, and that's this. Sine x over x equal 1 as x goes to 0, that limit. So you're going to have to convert this into something that looks like that, meaning whatever is inside the sine, I need to have on the bottom. And once it's in that form, you got the same limit if you're going to 0. Always think that way. As soon as you see a peculiar looking limit like that, you're going to think of getting it into the form of sine something over the same thing. Okay, that's just the big, that's the justification.
Wait, is the limit 1 or 4?
This thing is 1. The final answer to the problem is 4.
Okay.
It's because you got to multiply top and bottom by 4 to get that. Yeah, I may have misspoken there. Okay? I'm just filling in all the details. I'm not going to ask you to redo this on the exam every time. Once you get this, I'll let you say it's 1. But there are some instructors who do ask for that. Okay? The book doesn't point this out, which annoys me because he should. Because you need an argument to jump from this to say that that's really 1. All right. I'm afraid we're running out of time. Let me just see what homework, assign a couple of homeworks. If anyone wants to volunteer, I have homeworks set up. I'll take, okay. All right, let me just. All right. Okay, so in 1.4, we have problem 50. Yasser, okay, that was fast. Let me write that down. 1.4. Let me just take a very fast look and make sure I covered the material. Though I don't want to give you a problem if I haven't managed to cover everything. 1.4, number 50. This is hard material, by the way. Okay, you can do 1.4, number 50, Yasser. That's a good problem for you. Okay. 1.451. 1.451, this is a harder problem, but who's that? Ray Wang? Okay, I saw you first. That's going to be a little bit trickier, but follow the same guidance I just gave over here. When you see a screwy trig limit, you just got to get it in the form of sine something. Okay? Okay, I saw Ray, so you got it. Ray Wang. Okay, and let me see what else I can assign right now. Okay, that's really it, because 1.5 we didn't start yet. That's the next unit. So, and I don't have any more. Let me just make an important comment here. I don't assign tons of homework, as you see. Some people do, but realistically, limits are very hard. The only way to get good at doing limit problems is by doing tons of them. It takes practice. And as you can see already, there is no one way to do limit problems. Each one may require something a little bit different. Sometimes you got to factor. Sometimes you got to convert it like a trig problem like this, get it into the form you need. Okay? Sometimes you're lucky you can plug in. And we're going to be learning more tricks to do limit problems. Sometimes you multiply by the conjugate. So there is no one rule that's always going to work. So in that situation, the only way that you're going to get good is by sitting down and doing a ton more problems at the end of the section. Okay? Now, and I'll look at someone's asking about specifying which ones. Okay, Daniel, send me an email to remind me. What I'll do is I'll just look at the end of the section and I'll give you guidance on which ones are good for practice. I may end up saying you could try it all of number 5 through 17, something like that. But Daniel, send me an email to remind me to do that. So I'll take a look at the end of the section, but if you really, 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 really want to learn this very well, you do what I try to do always as a student, which is to do all the problems at the end of the section, okay? But certainly, we're going to be doing a lot of stuff in this course where what I just said is true. It takes practice. And limits in particular, limits are very difficult. And as I said, unfortunately, no one method always works. And that means it's a question of practice and experience. It really is. It's really, I mean, we're coming to topics soon where they're all always done the same way. That makes life easier. Limits are tough. They're tough from top to bottom. And as I said, we're just learning them in a very elementary form. Math majors in the junior year will really get hit with limits hard. Okay? So you've got to practice as many as you can. The more, the better. Okay? The idea is so that when you walk into the exam, you look at the problem, you say, oh yeah, I've done a bunch just like this. I know which way to go. Okay? All right, so I'm sorry, class is over. I'm sorry, I don't want to keep you over. We end at 4:05. Okay, I'm sorry for keeping you over a couple of minutes, but I'm just giving you some practical advice. The way to learn this stuff is to practice, practice, practice. It's not, math is not a spectator sport. Okay, it's like learning how to play tennis. You don't just watch videos, you go out on the court and you hit the ball. You got to pick up the racket. The more you do, the better. But send me an email to remind me, and I'll send you a guidance list. It's funny, in my linear algebra, when I teach linear algebra, I actually have that printed on the homework sheet. I say in parentheses, you should be able to do all of number 3 through 10, 20 or something like that. I didn't think of putting that here, but I should. Okay? So send me an email to remind me, and I'll send out some guidance about what problems you should try for practice. There are a lot of them, okay?